So it's my distinct pleasure today to introduce Karla Hemming, who is a professor of biostatistics at the Institute of Applied Health Research at the University of Birmingham in the United Kingdom. She is, when you look at what she's done, she's a real expert in stepped wedge randomized trials. And it's something where I think certainly I'm looking forward to hearing this and learning about them. And her title of her talk today is, when is a stepped wedge cluster randomized trial a good study design choice?
Okay, thank you very much for inviting me. It was slightly surprising, perhaps a little bit embarrassing to hear that you all actually based in Baltimore, and I'm really looking forward to the SCT conference. So we'll be in Baltimore in just maybe it's 10 days. So that was interesting little snippet of information that I just found out today. So today I'm going to talk about when the stepped wedge cluster trial is a good design choice. So I thought I might start with a bit of brief history. So the Gambian hepatitis intervention study was one of the first, if not the first, stepped wedge trial. It was an evaluation of the HBV vaccine in the Gambia. And in this trial, the vaccine program was phased out in a random, but phased way over 4 years, over the years 1986 to 1990. And their outcome was liver cancer. And they set up a national cancer registry specifically for the purposes of collecting that outcome in this trial with anticipated 30 years follow-up. So in their paper, they said that they used this type of study design. They didn't necessarily call it the stepped wedge design, but they said they used it because instantaneous universal vaccination in that country was impossible for logistical and financial reasons. And really what I want to do today in this talk is try to critically appraise these justifications and the reasons why people are opting for the stepped wedge design. So on the right-hand side, there's an illustration of how they implemented their trial. There were 17 vaccination teams across the 17 geographical areas in the Gambia. And over the 4 years, each of these geographical areas was randomly and also sequentially exposed, so that within that particular region, after that point in time, all of the babies born in that region would be vaccinated. And if a baby was born in that area before the vaccine program had been rolled out in that area, that baby wouldn't be vaccinated. And so around 60,000 babies were vaccinated and around 60,000 weren't. And the crucial thing here is that those 60,000 babies that weren't vaccinated will never be vaccinated. But after the rollout within the randomized evaluation, from that point forward, all of the babies were vaccinated. So this is the first stepped wedge trial design. And what I'm going to do today is really think about what are the appropriate justifications for using the stepped wedge trial. And I'll come back at the end and have a little think about whether or not the stepped wedge design there was an appropriate study design choice. So before we start, I thought I'd just introduce a bit of basic terminology. So this is a schematic representation of a stepped wedge trial. It's got 8 clusters and 5 periods, but that's just arbitrary. And we randomize clusters to different sequences. So in this design, there happen to be 4 sequences. Again, there can be various numbers of sequences. And the clusters randomized a particular sequence, and that sequence defines then the treatment sequence that cluster will be exposed to during the study period. So cluster 1, for example, is first observed under the control condition and then switches over to the intervention condition, and so on. And every time when a cluster switches over to the intervention condition, we call that a step. And we can think about clusters, but we can also think about cluster periods. So observations are clustered within a given cluster period. And this terminology was introduced in the CONSORT extension for stepped wedge trials back in 2019. So what I wanted to do today was to think about why we need good justification for design choice. So to this end, I wanted to start by introducing the main risks of bias for parallel cluster randomized trials. and then think through whether there are any additional risks of bias for the stepped wedge trial, and then consequently hypothesize from this that the stepped wedge trial is at greater risk of bias than the parallel design. And so therefore think about what are the appropriate justifications for using the stepped wedge trial, given that it might be at a higher risk of bias than a parallel cluster randomized trial. And then finally, just illustrate how these justifications differ from some common misconceptions of what are appropriate justifications. So the popularity of the cluster stepped wedge trial is definitely growing. So this is just a simple citation of, or search for citations of stepped wedge classified as randomized controlled trials in PubMed up to the end of May, beginning of May 2023. And we can see that from about 2010, the number of stepped wedge trials has sort of steadily increased year by year. So it's definitely on the increase. And then in 2017, a systematic review identified the reported rationale and the justification for the use of stepped wedge trials published at that particular time. So at that time, there were about 40 stepped wedge trials published. Now, interestingly, majority of the studies didn't actually report a justification or a rationale for choosing the stepped wedge trial. But of those that did, the most commonly cited reasons for using this type of design were that all sites get the intervention, that there were resource constraints, so some sort of staggering of the rollout of the intervention was required. And also a common reason was ethical reasons. Have a little think more later about what exactly that meant in this context. And then another justification was methodological or power and statistical reasons cited in a small number of those studies. So what I want to do today is to really break apart and tease apart these justifications and see if they are appropriate justifications. So why do we need to justify what type of study design that we're using? Well, the Council for International Organization of Medical Sciences say that we must have a good ethical justification for undertaking health-related research. And so it has to have scientific and social value. But for something to have scientific value, it really needs to produce a reliable result. And reliable results come from studies that are at low risk of bias. So we really need to be thinking about study designs that have low risk of bias. And so to this end, we can think about using the risk of bias tool, ROB2, the ROB2 tool. Now that was published in 2016, and there was an adaptation of that main guidance for parallel cluster randomized trials. And that guidance for assessing risk of bias in parallel cluster randomized trials categorizes the different types of bias into 5 main domains, and those domains are listed here. And I wanted to concentrate on just the first 2 of these domains because these 2 domains happen to be particularly problematic in cluster randomized trials. Now, that's not to say that those other domains aren't important, but I think it's probably safe to say that in cluster trials, the first 2 domains happen to be particularly problematic, and the other 4 domains are probably no more problematic than they are in other settings like individually randomized trials. So for the next few slides, I'll go through these 2 domains, give a bit of an illustration and some examples of what they mean and think about why they might be important. But I also want to introduce one other type of domain, and I've called this an analytical type of bias. Now, this is not included in the ROB2 tool, but it might be of importance in cluster trials, particularly when there are a small number of clusters. And hopefully it become evident throughout the talk why I think this domain is important. So the first domain is the bias arising from the randomization process. So in a parallel cluster trial, randomization simply refers to the process of allocating the clusters to the arms. So it's not the individuals or the people to the arms, but it's the clusters. So it's all about how we allocate the clusters. Now, the bias can arise if that allocation is either not random or it's not adhered to at the level of the cluster. So this means that any randomization has to have these 2 essential ingredients: Firstly, it has to be random. We're all probably very familiar with this. But this additional thing sometimes goes under the radar a little bit. It has to be concealed at the time of recruitment of the clusters. So how can randomization bias arise? Well, imagine that we're in this type of scenario, and these scenarios are a little bit extreme, but hopefully they'll illustrate the point. So imagine that we have been told that the clusters are about to be randomized, and one of the stakeholders in one of the clusters approaches one of the study investigators and says something like, I've been told that this cluster that's about to be randomized is really needy and it really needs to get the intervention. I think the people in this cluster really need that treatment. Can they please go in the treatment arm? And so someone else, perhaps in the investigators team, decide that they see that allocation list, they know the next cluster is going to be in the control condition, so they hold off randomizing this apparently needy cluster for a few days. Now, usually it's not explicit as this, but we do know, and there's lots of empirical evidence, that this type of subversion of the allocation can happen. It's usually very unintentional, but nonetheless, it can be consequential. Now, we've known about this in patient randomized trials for a long time, and we have managed to set up sufficiently rigorous processes to make sure that that type of subversion doesn't occur. And so good practice recommendations are that the person who undertakes that randomization should be independent. So for example, it's implemented through a trials unit or a data coordinating center. And that randomization must be concealed from the cluster until the cluster participation is ratified. And essentially, you have to apply that same level of rigor to that randomization process as you would in a patient randomized trial. Now, it turns out that in cluster trials, we're not quite there yet. And this type of level of rigor is not always applied in cluster trials. And actually, it seems like it's less likely to be applied with that type of rigor in stepped wedge trials. The second sort of bias, I think, is more important and perhaps even more underappreciated. So this is domain 1B, and it's called the bias arising from the identification of recruitment of participants within clusters. Now, this type of bias can arise when we have to identify or recruit the participants with knowledge of the treatment allocation. And this is the key bit. It's about recruitment of people when we already know what treatment arm they've been allocated to. And this can lead to differential recruitment and identification across the two different treatment conditions. It's also important to realize that this is about internal validity and it's not about external validity. It's sometimes referred to as selection bias. That can be a little bit ambiguous, also a little bit confusing because we tend to think of selection bias as something around external validity. And we might not be that concerned about external validity. We might prioritize internal validity. But in this particular context, when we talk about selection bias, we really mean a problem with internal validity. So this type of bias happens in a particular type of set of cluster trials. And it concerns cluster trials when we've got something called post-randomization recruitment, post-randomization identification of participants, and it's probably the most important source of bias in cluster randomized trials. It can be really hard to detect this type of differential recruitment across the study arms, but there are some ways that we can think about trying to identify it. So the first thing are that the big red flag is when we observe a difference in the number of people recruited across the study arms. Now, in this particular study, it's a cluster trial. We've been given information on the number of people in the two different treatment arms. There isn't very much difference between those two numbers here, so no big red flag. We also look at the characteristics of the participants recruited under those two different arms. And we can see 54% versus 57%, 18% versus 20%, so no hint of a difference there. But then we've got one of these categories, 27% versus 19%. And when we look at a baseline table like this, it can be really difficult. Is this just a chance in finding? Is it systematic? We know that we're not supposed to put p-values here. So this type of differential recruitment is really tricky to identify from baseline tables. But nonetheless, we know it exists because there's lots of empirical evidence. And so the first type of empirical evidence that we have about this, this type of bias is that when people have looked at many cluster randomized trials and aggregated the results together across many cluster trials, they see that on average, there are significant differences in the average age of participants in treatment and control arms. That doesn't happen when you look at individually randomized trials on average. So that's the first big hint that this bias really is problematic. The other type of way that we can get a handle on this type of bias is to look at the process evidence. So many cluster trials recruit participants after randomization. It's more than half of them, more than 50%. And of those that do recruit participants after randomization, most don't clearly report if this recruitment was blind to the allocation. And so therefore, most cluster trials don't appear to conceal the allocation at the time of recruitment. That therefore means that they're at risk of this bias. So how does recruitment bias manifest in practice? So again, a slightly extreme example here, but I hope it sort of illustrates the point. So again, in the setting where we're working with one of the investigators, and one of the investigators or the local PIs knows that their cluster has been allocated to the control arm. They're concerned about their sick patients, and so they decide that they're not going to ask their sick patients to participate. Yet, we really should be recruiting everyone who's eligible, and better still, we should hand over the recruitment to someone who doesn't know the allocation. So that's how it happens in practice. And there are some prevention and mitigation strategies. So prevention strategies, ideally we want to recruit all of the participants into our trial before we randomize. That's not always possible in cluster trials. We might want to blind the treatment conditions. That would prevent this type of bias, but again, it's not always possible in the types of interventions that we evaluate in cluster trials. So if we can't prevent the type of bias, we can take some mitigation strategies. And so mitigation strategies are minimizing the number of eligibility criteria, only have very objective eligibility criteria. That prevents that type of differential selection in part. And then we can also try to recruit participants into the study by someone who's independent to the trial and is blind to the cluster status. And that will minimize the recruitment bias. Now, in practice, those two things can be quite difficult to implement. And then finally, this analytical bias that I mentioned. So this analytical bias refers to a bias in the estimation of a treatment effect and its confidence interval. And it happens because we misspecify the statistical model. So we all know that any analysis of a cluster trial has to allow for the clustered nature of the design. In addition, again, probably underappreciated, when we've got a small number of clusters, we need to make something called a small sample correction. And essentially, that's using a t-test rather than a z-test. And we use k minus 2 degrees of freedom, where k is the number of clusters in our trial. So again, not very widely appreciated. Now, this sort of bias might be considered a fixable fault. It doesn't necessarily need pre-planning, but it is quite data greedy. But as I move on through the slides, hopefully it become apparent that these type of analytical biases are much more prevalent in stepped wedge trials. So risk of bias in cluster randomized trials then, in summary. So cluster randomized trials are at high risk of these types of biases, particularly the three biases that I've just mentioned: the randomization bias, the selection bias, and the analytical bias. So this figure here tries to illustrate that. It's a sample of 40 cluster randomized trials. They were all evaluating individual level interventions, so it might not necessarily be generalizable to all cluster randomized trials. And anywhere on this graph where you see green, that is low risk of bias. Anywhere on the graph that's red, it's high risk of bias. And the overall risk of bias is on the bottom bar, and each of the different domains 1 to 5, randomization process, identification and recruitment of participants, and so on, are on each of the other different rows. Now, it turns out that overall, for these 40 studies included in this sample, overall about 37 or 92% of them were assessed overall as having a high risk of bias. And most of this bias came from either the randomization bias or the identification and the recruitment of participant bias. So those are the two top bars here. So many of these trials, more than 50%, nearly 70%, were identified as having as being at risk of identification and recruitment bias. And about 50%, about half of them, had some sort of bias that could be attributed to the randomization process, either not being truly random or not being concealed properly. So that's the sort of state of play in parallel cluster randomized trials. And what I want to do next is to go on to think about how the stepped wedge cluster randomized trial might be at even greater risk of bias. Now, there's no formal adoption of the ROB2 tool for stepped wedge trials. So what I'll do over the next few slides is just outline what I think are some of the important considerations. So whilst the stepped wedge trial is becoming increasingly common, and it's got many characteristics in common with the cluster randomized trials, there are some significant extra complexities. And these mainly relate to what I'm calling temporal confounding within cluster contamination and deviations from the randomization. And so for the next few slides, I'm going to break these down slowly to try to understand how these additional complexities can lead to bias. So the first one, I'm going to start with analytical biases. So that was the domain that wasn't even included in the ROB2 tool for parallel cluster randomized trials. But I'm starting with it first because I think it turns out to be the most important type of bias in stepped wedge trial. So remember, this is just around the risk of bias that we get because we don't estimate properly the intervention effect or its standard error or its confidence intervals. So we can think about breaking this down into two components. Firstly, the bias, so bias of the point estimate, and secondly, the standard error, perhaps less important. Now, it turns out that we can get a point estimate, so get true bias in our estimate of the treatment effect when we're using a stepped wedge trial. And this arises from problems with something called secular trends. And it can transpire that we might identify an apparent effect due to the intervention, but actually it's just an effect due to the natural changes over time. And over the next few slides, I'm going to try and illustrate what I mean by that. There is this additional complexity of just making sure that we get our standard errors estimated correctly. It is more complicated. It's more complicated than a simple exchangeable correlation. So we need to include random effects for our clusters. It turns out it needs to be slightly more complicated than just including random effects. But again, this is like a fixable fault. As long as we're aware of it, we can make sure that we get the right standard errors. But this other issue with bias in the point estimate turns out to be more problematic. So why is time a confounder? Why are these secular trends important? Well, it's useful to go back to think about what the stepped wedge trial looks like again. So we've got 6 clusters in this illustration and 7 different time periods. And the blue represents the time periods when the intervention is rolled out, and the white represents observations that have been collected under the treatment, the control condition rather. Now remember that a variable is a confounder if it's associated with both treatment and the outcome. Now if we think about time, could time be a confounder here? Well, time would be a confounder if it was associated with both the treatment and the outcome. Now, when we think about breaking down a confounder like that, we see that in a stepped wedge trial, time is a confounder by design, because the likelihood of a treatment, of somebody being treated or an observation being exposed to the treatment increases with time. So the intervention is rolled out sequentially over time. And if in addition, the outcome changes over time in absence of any intervention, so there's just a secular trend there, this will mean that time is a confounder. Now, whenever we set up a randomized trial, we try to remove our confounders. The act of randomization prevents us having to worry about confounding. But in stepped wedge trials, it's the opposite. It can induce confounding. So here's an example of how it can be particularly problematic. So these are the results from a stepped wedge trial. The outcome here was, or the setting is in maternity, and it was trying to prevent women from having their babies over term. So the intervention was some sort of training targeted at the midwives, so it used a cluster randomized design. And the outcome was whether or not the women had a membrane sweep. And so this little bar chart here shows the proportion of women who had a membrane sweep under both control and intervention conditions. And the objective here, or the hypothesis, was that this intervention, this training program, might increase the proportion of women who were having their membrane swept. So when we look at these two bars, we see that the control is around 45% and the intervention is at around 47%. And this provides an adjusted relative risk of about 1.06. So saying that the intervention seemed to improve the likelihood that a woman had her membrane swept. Now, it's not statistically significant, but if we can just ignore that. But overall, this is giving us the sort of hint that this intervention is working. So it has an apparent positive effect. But remember, this came from a stepped wedge trial. So let's have a look what happened over time. So on the right-hand side of the on the right-hand side of the figure, we've got the week of the study. The study was run over 40 weeks. It was a stepped wedge trial. And the black simply shows the proportion of women who were having a membrane sweep over the duration of the study under the control condition. So the black is just, in absence of the intervention, it's got nothing to do with the intervention. It's just the proportion of women who were having a membrane sweep whilst they were under the control condition. And we see that this started off at about 40%, 0.4, and it steadily increased to around 50%. So what was happening here? There was a secular trend. The proportion of women who were having this outcome was gradually changing over time. And when we adjust for the fact that there was a secular trend, the adjusted relative risk reduces to 0.088. Again, not quite statistically significant, but just focusing on the point estimates, adjusting for that secular trend completely reversed the effect of the intervention. So now it looks like an apparent negative effect. So trying to convey the meaning of results from a stepped wedge trial when there's an underlying secular trend can be difficult. It can be confusing. It can look like there is a positive effect when there might be negative and vice versa. But we can adjust for these secular trends, or can we? So in the example I just showed you, I gave you an adjusted result, adjusting out this secular trend. But unfortunately, it's not as simple as that, because we have to make assumptions around what the patterns are of these secular trends. And most step wedge trials follow analysis published by Hussey and Hughes back in 2007. And they made that model makes quite strong assumptions about the nature of these secular trends. And I've tried to illustrate on this graph here what assumptions are made. So on this plot on the left-hand side, we've got three different clusters, a solid line and a couple of different dashed lines. They each represent a different cluster. The black represents what might be happening to that cluster under the control conditions. So just a secular trend, what is happening over time to the outcome in absence of the intervention. So each of these clusters has some sort of secular trend going on. Roughly, the incidence of this outcome is gradually increasing. And then we have an effect of the intervention condition. So the treatment condition, denoted by this triangle, it shifts the outcomes under the treatment condition, and then they're shifted now to these red lines. So three different red lines representing three different clusters here. We make two assumptions here. The first assumption is that those black lines all follow the same pattern. So every one of those black lines is following the same trend. They don't necessarily have to start off in the same position, but they're all following the same trend. And this is known as the common secular trend assumption. And almost all stepped wedge trials end up making this assumption, and it's very difficult to deviate from that assumption. So that's the first assumption we end up making. The second is that there is a single shift of that intervention, and that single shift or that single impact of that intervention, that delta, remains constant throughout the duration of the study. And again, almost all stepped wedge trials make that assumption in the analysis, but it also can be quite a difficult assumption to test, and it's probably not always going to be an assumption that's very tenable. So that's the problem. So what does it mean in practice? In practice, it means that when we use the stepped wedge trial, we must adjust for time trends because there can be time confounding effects. But if we use a model-based analysis, we make these assumptions of a common secular trend and a common treatment effect. They're unlikely to be tenable in many situations, and more importantly, perhaps, we can't test them. So it's worth also noting that these types of biases are unlikely to affect parallel designs. Can we prevent these types of biases? Well, there are a couple of things that we can do. If we randomize a large number of clusters, this is probably going to help randomize those different types of trends across the different sequences. And the other thing that we can do is we can include more homogeneous clusters, trying to make those clusters meet the assumption of a common secular trend. At the analysis stage, we must adjust for secular trends, and then we also have to allow for these non-exchangeable correlations that I mentioned earlier on, just to make sure that we've got our standard errors correct. They're probably less important, I think. And we also should use flexible models. One thing that I would probably advise against is testing whether or not time is a confounding effect and adjusting for it based on a statistical test. It's probably not the best way of determining whether or not time is a confounder. It's probably safe to always adjust. Then there are different ways that we can adjust for time effects. So I've listed 4 here. The second one is this common categorical or common secular trend effect known as the Hussey and Hughes model that I just depicted on a few slides before. So that's the most common type of assumption that is made, assuming that there's a common secular trend. We can perhaps do something that might seem a little bit better. That's known as number 1 here, the cluster-specific nonlinear effect. Sorry, that should say linear, not nonlinear. So a cluster-specific linear effect. So every cluster is allowed to have their own trend, but it has to be linear. And it's not possible to have both a cluster separate effect that's also nonlinear. There's not enough data, not enough degrees of freedom in these models to be able to do that. That is infrequently used anyway. But there are other things. The permutation-based test is probably robust to misspecification of these time trends, and also models that allow for time by treatment interactions to allow the possibility that that effect or size of the treatment might change over the duration of the study. But unfortunately, each of these ones, whilst they increase in their robustness, they also increase in their sort of data greediness. So if we set out and we design our trial as a study where we're going to assume a common categorical effect or a common secular trend and use that Hussey and Hughes approach, it probably will turn out that if at the end of the day we wanted to use a permutation type test, we would sacrifice quite a lot of power. So it's really important to think about these things up front. So this added complication of a time on treatment effect. So I've tried to illustrate what's happening here with this example where we've got a stepped wedge trial with 7 or 8 different periods. We've got a time period effect or a secular trend happening under the control condition on the left-hand side. So this is what we think our secular trend is going to look like over time. And then we can also try to estimate a time on treatment effects. So this is like an interaction between how long that cluster has been exposed to the intervention and what their treatment effect is at that particular time. And so in this example, we see that we might start off with quite a large treatment effect immediately after the intervention has been rolled out. Sorry, a small effect, and then that starts to get larger as time continues. So we might expect something like that to happen, where we're constantly reinforcing our intervention. Now, the problem is, although this can sometimes seem to be very intuitive, we might have very strong reasons why we might expect our treatment effect either to get larger over time or to decrease over time. It can be really difficult to try to model both of these things at the same time. There's just not enough degrees of freedom in our data sets to allow us to do both of them properly. And again, this can lead to bias. So there are quite a number of different papers in the literature trying to explore different ways of modeling these time effects in cluster randomized trials. So I don't want to give the impression that it's not possible to robustly model these time varying treatment effects and these secular trends and to allow them to differentially affect the different clusters. But it's not straightforward, and it takes up lots of data to do it properly. So a few papers here that have evaluated some different approaches to this. So then in summary so far, what we find is that stepped wedge trials make strong assumptions about secular trends. It might challenge the strength of evidence that we get from that design. Parallel cluster trials don't have to make those same assumptions. And there are also different other risks of biases that I haven't mentioned very much here. That probably are going to be prevalent in the stepped wedge trial, but not under the parallel design. And these are within cluster contamination and deviations from the randomization schedule. So two other things that might also be more problematic in the stepped wedge trial. So because of all of those reasons, we must really be careful about when we use the stepped wedge trial. So when can we use it? So what I'm going to do over the next few slides is try to give some reasons for justifications, good practice reasons for when it might be a good study design. Perhaps say at the very beginning that they're not hard and fast rules, and probably the more of these requirements that are satisfied, the more likely it is to be the right choice for that particular setting. And then finally, just run through a couple of misconceptions. So what do we need to justify in the stepped wedge trial? Well, we obviously need to justify the use of cluster randomization, but let's suppose that's given, because all this is within the context of needing to cluster randomize. So then that leaves us with two additional things. We need to justify rolling out this intervention to all of the clusters, and also for the staggered rollout of the intervention. So those are the two additional things that we do in this stepped wedge trial that we don't do in the parallel design. So what I want to do then is to think about 4 different possible justifications that I've listed here, and I'll go through each of these on the next few slides. And although I'm putting them all up here as possible justifications, I think it's important to underscore how all of these can be tempered by disadvantages, and so require very careful consideration before being used. So the first possible justification is that the stepped wedge trial provides the means to conduct a randomized evaluation, and that without the stepped wedge trial, it wouldn't be possible to conduct a randomized evaluation. So how can this occur? Well, sometimes it might occur because the rollout of this intervention has to be sequential because there's a limited resource or limited capacity to roll out this intervention to the entire health system at the same time. Or perhaps because there's the possibility to learn from a gradual implementation of this intervention in such a way that the intervention might be adapted as it is learned. Now that can bring added complications, but let's put those complications to one side. Now suppose that we are in that setting. That can seem like an adequate justification to use a stepped wedge design. After all, it's a randomized evaluation, and without that randomized stepped wedge design, perhaps we wouldn't be able to run a randomized evaluation. We may be forced to use a before and after study or something like that. However, if we can convince our stakeholders to randomize this order of the rollout that we have to do if we're going to use a stepped wedge trial, then it's probably possible that we might also be able to convince them to randomize to a parallel design. And so, although on the one hand, this can seem like an adequate justification, if we're prepared to push stakeholders a little bit more, they may also see the benefits of using a parallel design, and that would mean that we wouldn't have to deal with these added complications of the stepped wedge trial. So that's the first possible justification. The second possible justification is that it might facilitate the cluster recruitment. So it can be really difficult to convince stakeholders, gatekeepers as they're sometimes called, to participate in a randomized trial. Sometimes it can seem the case that stakeholders might be more amenable to participating in the trial if they're guaranteed to receive the intervention. Now in the stepped wedge trial, everyone gets that guarantee. Everyone knows that at some point in time, their cluster is going to get the stepped wedge to get the intervention. Not every participant does, not every individual does, but every cluster does. Now, it can sometimes be the case that stakeholders and gatekeepers, the cluster gatekeepers, they have their own a priori beliefs about this intervention, and they can just naturally think that something new is going to be better, and that therefore can mean that they're more likely to participate if this randomized trial is designed as a stepped wedge trial. So we sometimes refer this to increasing the social acceptability or the appeal of the stakeholders. But there's a problem with this as well, and that is that we really should attempt to educate and demonstrate that stakeholders may think that this intervention is going to be effective, but actually we're running a randomized evaluation here, so it's unknown whether it's going to be effective. And if they're fully informed of that equipoise, then other alternatives such as a parallel design and maybe even a waitlist design perhaps might be acceptable to the stakeholders with that improved knowledge. So another justification, but again with a big caveat. The third potential justification is that it creates a logistically feasible design. Now remember back to those common reasons why people are using this type of design. This indeed was one of the cited reasons. So there can again be limited resources or capacity to roll this intervention out to the entire health system. So for example, maybe we've got 10 clusters that need to get this intervention, and it might not be possible to roll out this intervention to those 10 clusters all at the same time. Again, can work, but again, there are caveats there. So running a stepped wedge trial in itself can bring about its own logistical issues. Some of these logistical issues that we face in stepped wedge trials aren't there in parallel designs. So for example, we might have to organize all of the research ethics approvals for all of the centers in advance and make sure that they're all ready to start the study at the same particular point in time. We don't have to do that in a parallel design. In a parallel design, it is possible to have our clusters come on board as and when they've got their own center level approvals. But in a stepped wedge trial, all of those clusters need to be there at the get-go. So that brings its own logistical challenges. And then the other thing to note is that we can also run a parallel cluster trial with staggered cluster recruitment. And this example here of a trial called the emotive trial tries to illustrate how we can do that under a parallel design. So this is an example of a parallel design where we stagger the recruitment and stagger the rollout of the intervention. We might think of it as something like a batched cluster design. And so in this type of design, clusters are randomized in batches as and when they are ready to commence a study. And this therefore means that not every cluster needs to be ready to start the study at the same point in time, and not every cluster needs to get the intervention at the same calendar point in time. So this is another logistical advantage of the parallel design. And then finally, justification 4. So this justification that is often put forward and can sometimes be true is that it has increased statistical power. So it's a sort of methodological reason. Now, sometimes this can be true, and it can be particularly true when we've either got a small number of clusters, perhaps because there's only a small number of clusters who are available, or a small number of clusters that are willing to participate, or maybe a limited trial budget. Now, under those circumstances, sometimes a stepped wedge trial might seem to achieve the desired power with fewer clusters than the parallel design. It turns out, though, this only often holds when there's a small number of clusters. But we also have to remember that whilst it can look like they are a more powerful design, this is probably at the cost of making quite strong assumptions. And in those cases where we make those assumptions, as we've seen over many of these slides in this presentation, there can be this increased risk of analytical bias. So again, another big caveat. There are a couple of other considerations. So in stepped wedge trials, we have to make sure that the study duration is going to be longer. And that might not always tie in with funding constraints. Whether or not the parallel design or the stepped wedge design turns out to be shorter or longer in duration really does depend on the nature of the setting. And it's not always the case that the stepped wedge turns out to be longer, but it often can be. And the other thing to think about is how long it's going to take us to realize the effects of the intervention. If it needs a lot of time to start working and affect our outcomes, then the stepped wedge trial might not be the right study design. And that can be particularly the case for complex interventions. So finally, what's this misconception? So we'll often find in the literature, both methods and applied, that people use the stepped wedge trial because they think it's ethically the right thing to do. And you might see something like this quote here: it's ethically appropriate when the intervention is expected to do more good than harm. But, you know, if we think that this intervention is going to be good to give everybody in our trial, all our clusters and all our participants, then we really should be giving everyone that intervention. And actually, if we're in that situation of equipoise, that's when we want to do a randomized evaluation. And if we are in that setting of equipoise, then it's not appropriate to say that this intervention is expected to do more good than harm. After all, that's what we're trying to test. So that's a common misconception that we often see in the literature. So back to the GAMBIA study. So remember, they said that they used this type of study design because instantaneous universal vaccination in that country was going to be impossible for logistical and financial reasons. So first thing I think to say is actually there are risks with all types of trial designs. This trial hasn't reported yet. Remember, it was anticipating 30-year follow-up, possibly never will. So there were problems with running this trial for that longer duration. So cluster randomization was definitely necessary. They were interested in both the direct and the indirect effects, even though it was an individual level intervention. Was the stepped wedge trial justified? Well, it's possible that there was evidence of effectiveness in other settings. So the fact that every cluster would ultimately receive that intervention was probably appealing to the stakeholders, probably enhanced the likelihood that it would be possible to use a randomized evaluation here. And perhaps more importantly, it did allow a randomized evaluation. And without that randomized evaluation, they probably would have used a non-randomized type of study design. So probably it was justified in that situation. It is hard to say, though, of course, without all that the context and the decision-making processes that went on at the time. So then in summary, stepped wedge trial, its use is growing. It's definitely very popular at the moment, but its risks of biases are probably going to be larger than those that we see in a parallel cluster randomized trial. So the consult statement for stepped wedge trials said that we should justify why we're using that type of study design. And I think what we're trying to argue here is that just because it's popular and just because it's novel, those shouldn't be the reasons why we adopt it. And in many cases, the parallel cluster randomized trial, that old sort of favorite, is probably going to be the preferred trial design. So just a few useful resources on that slide. And I'll leave it there. Thank you.
Well, that was outstanding. And we are now open for questions, if anybody has any.
Thank you, Douglas.
Michael, I see a hand up.
Hi, yes. I was wondering, I've been following a lot of the recent developments in the difference literature. And I was wondering if you can kind of talk about how step wedge RCTs for control trials compare to differences when one might use one might use the other, beyond just the randomization element. Thank you.
So I think that speaks to two different disciplines working in two different areas at the same time. And I think when I've looked into that literature a little bit, it's been in the sort of economics literature. And I think which two different disciplines are probably doing two different things in parallel. And I found that it's been really hard to try to understand what they're doing because they're using different terminology. It's really difficult. When they say difference and difference, I initially thought that they meant taking the two differences and then taking the differences between those. But I think they're also using the term difference and difference in a way that we would not use that term in the health-related research. I think there's definitely a lot to be learned. And to be honest, I have looked at it a little bit and I found it very hard to get into. Yeah,
that's actually
a really good question.
Thank you.
Ian.
Hi, Dr. Hemming. Thank you for that. That was great. Question. It's been a while since I've read the risk of bias tool for the design that you presented on. In the second domain where bias arising from knowledge of the treatment assignment, identification of participants with knowledge of the treatment assignment. Is there a lot of empirical evidence that that domain was based on? I mean, intuitively, it does make a lot of sense that there would be bias arising once participants are identified based on that, but did that stem from a lot of empirical evidence?
So, so if you can break the evidence for that risk up into two components. Firstly, the sort of purely empirical, and what people have done there is they have taken large samples of cluster trials. I think they had about 100 or 200 cluster trials. They looked at the differences in the age between control and intervention arms, and they sort of meta-analyzed those differences across all the cluster trials. And when they meta-analyzed all those differences in age, you would expect there to be on average no difference. But when they meta-analyze those differences in age, a common characteristic that is reported in most trials, so almost every trial was able to contribute to that meta-analysis, they found if it was a cluster trial, then on average, there were differences in ages. And if it was an individually randomized trial, they found that on average, there were no differences. It was randomized, so you wouldn't expect. So that's the first part of solid evidence that there is. The second solid set of evidence is just a process type evidence. If you look at these cluster trials, you see that an awful lot of them recruit people after the clusters have been randomized and they're non-blinded. So it's not direct evidence, it's more like an indirect evidence.
Okay, so so it's indirect, so as you're saying, but it's they weren't able to explicitly make the link that the participants were identified after the knowledge, and those were the trials specifically that had differences in ages per se.
No, they haven't done that. No. Yeah.
Thanks.
That's really difficult to do.
Yeah.
You can't. I mean, it's almost impossible to do that, I think. Well, yeah. I think so.
Or at least very hard.
Yeah.
Other questions? And since I can't see everybody, if you have a question, just go ahead and speak up.
Well, somehow I have knocked my camera, so I can't turn it on again, but I wanted to thank you for what a wonderful talk, and just brought up a lot of kind of thoughts about, fundamental analyses in any clinical trial, which actually just make me more nervous about them. One thing, and maybe I'm of the frame that I thought of where step wedge designs would be useful sort of as a confirmatory step before something that had, or a program or a treatment that had met our conventional evidence standards. But if in general, like the vaccine, if you have to roll things out, why not learn more? Sort of a learning healthcare system. You seem to argue against that a little bit, or maybe I misinterpreted.
No, I think I probably do argue against that a little bit. Say if it was a vaccine, no, if you really are still in equipoise, you shouldn't be. You should be randomizing, and if you're not in equipoise, you shouldn't. And if you're going to randomize, then why not choose the best randomized design? Why use a randomized design that might induce a bit of bias? So I think with those sorts of interventions, I think I'm definitely over the side of like, it's not a great design. I think maybe where there's a bit of gray area is a sort of like implementation type of interventions. So we might have like a bundle of interventions. We know that individually they're all supposed to work, but actually what happens in practice is people don't use them. And so then our intervention is not really each of the separate components, but it's this intervention. And then I think we probably get back to the same issue, that we want to evaluate whether that education package works, that bundle works. And it's no longer the separate components, but it's something bigger than that. And so then again, we're in equipoise. And if we really want to evaluate it properly, then why not choose a design where we're at lower risk of bias? So I think you probably did interpret me as I wanted to be interpreted. I think maybe it's quite a strong line, and perhaps not everyone would agree with that.
Well, thank you. And indeed, many of us will be at the Society for Clinical Trials in next week, which is basically down the street from us. So
Yeah. Yeah.
we'll look for you. And I hope I have an opportunity to either buy you a cup of coffee or lunch or
Thank
something.
Thank you. There's a whole session or a couple of sessions on stepped wedge trials there.
Okay, great.
Well,
Thank you.
This was terrific. I think our time is now up. I want to thank you very much for talking to us. I think it was incredibly informative, and I, like Janet, look forward to meeting you in person at the Society for Clinical Trials meeting.
Yeah. Thank you very much, Anna. See you in a couple of weeks.